Sorry. No.
Welcome to Theoretically Podcasting. This is your host, Vasu Sham, and today I am joined by my friend and colleague, Yigit Yargic. Welcome, Yigit.
Thank you, Vasu. I'm Yigit, and I'm happy to be here.
So Yigit is a researcher at Microsoft working on matrix models, but we will have another episode where we explain exactly how that came to be and what exactly it is that he is doing. And I suppose I'm also doing because I'm his collaborator.
Yeah, so we know each other from PhD,
Yes.
and we are also working in a project at Microsoft together that we'll talk more about in another episode.
Yes. So we're looking forward to that. However, the conversation today is going to center on the topics of Borel resummation, resurgence theory, and alien calculus. And that very last phrase, yeah, so that phrase, I guess, caught your attention. It caught my attention too when I first encountered it during my PhD. And I thought it would be a great gag to come down to the cafeteria of the institute where I did a PhD, Perimeter Institute, and tell everybody at the table that I computed the alien derivative of some such thing.
Definitely a good conversation starter.
But unfortunately, I didn't have the discipline to follow through with this gag, and eventually I just finished my PhD and never got to do it. So I decided that I would subject Yigit in person to it now and all of you on the internet. So prepare yourselves.
So I'm also going to be learning about the topic.
Yeah, so we literally decided a few minutes ago that this is what we will be diving into today. So I guess for starters, I should explain the physics motivation for why we use resummation techniques. So in quantum mechanics and quantum field theory, we are often in a situation where we have to resort to perturbation theory to gain some control over the problem. Right? Now, it's great up until the point that you realize that the output of perturbation theory is typically just an asymptotic series with zero radius of convergence. And even all of your normalization theory, what it lets you do is render like individual terms in the series finite, but it tells you nothing about the sum. And in fact, the sum typically has a growth of its various terms, as in within the sum, that are like factorial with respect to the order. So that just grows way too fast to be able to sum it. And of course, it's just going to have a zero radius of convergence. And the question is how to do better than that. So that is where the general topic of Borel resummation comes in. And the idea is, first, given a sum that is asymptotic in this way, how do we obtain another sum, which kind of looks like the original one, that has a finite radius of convergence, right? And then the idea is to undo this transformation and improve our original perturbation series. And that might sound confusing at this point, right?
This is also sound related to your last episode about the zeta regularization.
Good point. Now, zeta regularization in and of itself is just an object that lets, or it's a technique that lets you render particular terms in a sum finite. It is, of course, itself a representation of a kind of sum. And there you rely on some analyticity properties of the integral representation of the sum in order to obtain a finite result through analytic continuation. So it is very much like what you do in this context.
But now we are working directly with the sum itself.
Yeah, exactly. But now it's not a sum over modes. It's really like the small parameter we're talking about here is, for example, the coupling in some observable quantum field theory, or even, say, the ground state energy of some quantum mechanical system. And what we'll see is that once we go back from the new series we generated that has a finite radius of convergence to the improved perturbation series that we started with, we will have contributions there that look non-perturbative or that are non-perturbative. So resurgence theory allows you to start with perturbation theory around a trivial vacuum and obtain information about non-perturbative sectors just through some transformations. So that's a remarkable feature of it, right?
So resurgence theory is this procedure, or what is it?
I mean, it's a broad term that refers to this procedure and procedures like it. I won't try and go into a technical definition of it, but the object of study are what are called resurgent trans series. And there's a mathematical literature associated to the study of these series, which is sort of spearheaded by Ekel. And if you translate from French what he called this subject, it's alien calculus. So that's where the alien derivative comes. So the aim of today's episode will just be to compute one alien derivative at least. So we'll be happy if we capture one alien, we'll be happy. So first, let's begin by looking at what an asymptotic series technically is, right? And then we'll go into basically what we need to do in order to tame an asymptotic series. So great. So here I'm using Marcos Marinho's notes on instantons and large N. The title is large N and instantons. And it contains a section on Borel resummation. But I'm just using it to lay out some conventions and definitions. So the basic idea of an asymptotic expansion is that we have a certain series for which the difference between the function s of w and the sum we're using to define it up to order big N, all multiplied by w, the expansion parameter, to minus n, in the limit as w goes to 0 equals 0. Right? So basically, it's like saying that we have a good approximation of s to order n, right? And that's the most you can hope to obtain in a lot of examples in quantum field theory, right, where you use perturbation theory. Now, what is the peril, right? Like, why is this, or what is the nature of the trouble that we end up with in trying to make sense of the sum? Well, typically what you find, and I'll explain what is meant by typically, but what you find in a lot of examples is that you have terms in this series where the coefficients grow factorially in the order, which, I mean, is pretty bad. Yeah, right. I mean, it's terrible. And now, what we can do is measure the error in our nth order truncation of the power series when we compare it to the function we're trying to approximate. So the
because with it, when it goes with n factorial, there's the radius of convergence is 0.
It is 0, yes, yes. So I mean,
so these are not technically convergent series.
Exactly. They're formal series at best. So there's a definition of a strong asymptotic series for f if for all n there exists this bound, right? That the difference to order n is captured by something to w of w to the power n plus 1, where the proportionality factor of the bound is a power minus n big N factorial. Now, the issue with that is f and f plus something times e power minus a over w will have the same asymptotic expansion, because to no order in the perturbation series will you discover this kind of function. Right?
So there's a degeneracy in the set of functions that we can approximate to.
So what we're beginning to discover is what's known as a non-perturbative ambiguity. So let's dive into that. Now,
in what sense is it non-perturbative, or maybe that's something you're coming to?
Yes. No. I mean, at least at this level, we can see that the object here, which it has an essential singularity at w equals 0, is something we would never discover in perturbation. And so you need something non-perturbative to tell you what it should, what its value should be.
I mean, with this essential singularity, the the expansion around w equals 0
This
is
is always zero. So you'll never see it, right? Now, let's ask, what is the optimal truncation? This is what Marino moves to, right? So he poses this problem in an alternative way, which is actually, I think, instructive and relies on a neat trick. So he says, say we have function f, which is a strong asymptotic expansion around w equals 0. And what we want to do is look at the order n, so the truncation order, which is optimal, right? So we want to know, like, okay, how good can we get this series to be, like the series representation of the function to be?
So this means it's not that the more terms we have, it's the better. There is a limit to including more terms and getting it better. There's a limit to that.
Very good, very good. And we can make that precise here. So it says that to obtain this optimal truncation, we saturate the bound, right? And we ask what n minimizes this, right? And here we can use Stirling's formula to approximate the factorial. And what we can then do is look at the saddle point evaluation of this object, right? Because we want to minimize with respect to n. And so there's going to be a saddle point of this object at n star that equals a over modulus of w. Now you plug that back into the error, which was Cn w power n, and you find e to the power minus a over mod w.
Let's go through this maybe a bit slowly. So we had the bound.
So we had our bound
at equation 4.37. That
yes,
no, yeah, so it's 4.38. That it wasn't growing worse than exponentially. So it was worse than factorially, so to say. This was the bound. So now in the 4.40, we have saturated this bound. That is, how close are we to this bound, to having such a bound, which contains a factorial in n. We are looking for some, with large n, we are going to use the Stirling approximation and then take the derivative with respect to n to minimize this bound with respect to n. I understand.
Yeah. So n will disappear in favor of everything else, which is a and w. And what we find is that the error c at that optimal value of n times modulus w to the power n is e power minus a over w.
This is the saturation point with the...
Yeah. So the maximal resolution you can expect is of this order. Right. So that's like what you're missing, so to speak.
The order at which we are closest to the series being actually
exactly the good representation. So this is a non-perturbative ambiguity. This is why it's called non-perturbative ambiguity. And now the purpose of resummation theory is to resolve these ambiguities. So let me just jump to a physics context. And here, I plan to go over this paper thoroughly towards the end, but let me just flash a section of it, or at least one explanation from it, which is this nice paper by Alex and Milakin on the Lagrangian description of Borel resummation. Right, so we're now in the physics realm, but what I wanted to start with is an explanation here about what's called the Bogomolny-Justin regularization, which is like a simple manifestation of non-perturbative ambiguities just in quantum mechanics. Right, so basically the idea is, let's take a particle in a double well, and we're doing a calculation of, say, tunneling rate or ground state energy using the Euclidean path integral, which is why the terminology involving integration cycles is used here. So here's okay, so there's a bit of an explanation about what the Borel sum is, but let me just give some motivation before jumping back to what the Borel sum is, right? So let's read this section about the non-perturbative ambiguity that arises in a coupling expansion of, say, either a transition amplitude or a ground state energy in the problem of having quantum mechanics with a double one, right? So he says that this non-perturbative ambiguity arises because the instanton and anti-instanton attract one another, and one cannot assume that they are well separated. Technically, the problem is that the integral over the distance between instantons is not well defined. The way out is to analytically continue the expression for this amplitude to negative values of the coupling. Then instead of attraction, there'll be repulsion. And we are able to compute the integral over the separation. And then we rotate the coupling constant back to its original positive value. This is called the Bogomolny-Zinjustin prescription.
Similar to how we define the Riemann zeta function for
for negative values of
negative
the exponent.
And
or
then
in other words, in positive
extend it to positive exponent.
Yeah. So now, the final answer is not analytic in the coupling. Typically, it has a logarithmic branch cut. So rotating G back will produce an ambiguity, which he then says here cancels the perturbative ambiguity, which came from originally complexifying the coupling constant, dividing every term in the power series by n factorial, and then doing a Laplace transform to come back to the original coupling expansion. That's the Borel trick. So I haven't explained that yet, but here is basically the sort of vision for where we're going, right? Like what we're getting to do. So the idea is that this game with instanton anti-instanton configuration and the fact that you have to kind of like complexify or analytically continue the coupling and then go back generates another ambiguity which cancels the ambiguity of doing the Laplace transform to go back to the original series. And then he says the instanton anti-instanton contribution manifests itself on the Borel plane as a simple pole on the positive real axis, which is why there's two ways to avoid it, and that's why there was an ambiguity perturbatively. And the basic idea is that the fact that these two ambiguities cancel each other in the final answer means that they should cancel before we perform the inverse Borel transform. So we're just on the Borel plane. And so it means that this contribution can be evaluated through a sort of median resummation procedure on the Borel plane itself. So non-perturbative ambiguities present themselves as ambiguities in analytic continuation. The purpose of analytic continuation is to render asymptotic series as ones that have finite radius of convergence. So this is just a motivation for it, right? But let's go back to this Borel part.
So let me try to recap this last part. We evaluated this series with a negative value of the coupling so that it is a repulsing potential, and we have we can separate the instanton and anti-instanton. But if it is a positive coupling, then not only is it not directly definable, but it also has a branch cut ambiguity that is also related to this exponential, the essential singularity term ambiguity in the Borel sum.
So there's two things going on in this specific example, which is both the logarithm and the exponential that both have an essential singularity at g not equals 0, right? So in general, these trans series tend to have contributions involving this kind of exponential and the log. And these logarithmic terms always arise from what are called quasi-zero mode contributions. And this is a sort of paradigmatic example of a simple quasi-zero mode integral. But now let's go back to what Borel resummation is in the first place, right? Because we've talked about just wanted to give meaning to a non-perturbative ambiguity in physics, because computing the amplitude arising from there being an instanton and anti-instanton, it's a non-perturbative effect, right? Like the instantons are non-perturbative.
Yeah.
So that was just like, I just wanted to jump to this to give some motivation as to why it's called non-perturbative ambiguity. And we sort of looked ahead to see how to resolve them. But first, we have to look at what the Borel resummation procedure is in the first place, right?
This was the motivation, and now
We'll
what
jump
is the
back.
Borel sum?
Yeah, good. So the Borel sum is given by a simple transformation of the original series. And the idea is take every term in the series and divide by factorial of the order. Because that was a problem to begin with.
It was growing with a factorial term.
So just divide by factorial.
Just remove it.
And then just, well, all of a sudden, B sub S of Z has a finite radius of convergence, right? With rho equals A being that factor that appeared in addition to the factorial, right? We had A power minus N, and we had N factorial. Now we just have A power minus N, so great, right? So this defines an analytic function in the circle mod Z less than A. Right? So A sets the radius of convergence. Now, Borel, apparently, thanks to Wikipedia, we know this fact. So Borel, then an unknown young man, now he was still unknown to me relatively recently, so I can relate to that, discovered his summation method gave the right answer for many classically divergent series. He decided to make the pilgrimage to Stockholm to see Mittaglepper, who was recognized the Lord of complex analysis. Mittaglepper listened politely to Borel, to what Borel had to say, and then, placing his hand upon the complete works by Weierstrass, his teacher, he said in Latin,
The master forbids it.
Nice. This is great. So apparently, Catch quoted, this was quoted by Reed and Simon, but Catch was the one who recounted this. These kinds of things tend not to happen, so it's fun to like hear these
Lord
stories.
of complex analysis.
They're all gone now. So, or maybe not. Let us know in the comments. Who do we take our bad ideas?
Lord of non-perturbative analysis to make the pilgrimage to.
I think we know some people, but we'll bring them up soon. So anyway, best thing to do, consider an example, right? Alternating sum of factorials times W to some power N. Just, straight up problematic sum, which nobody would expect to converge. Borel resummation is very easy. Divide by N factorial.
Get rid of the...
And let's briefly jump to Mathematica to convince everyone that this has a simple representation. So what was it? We have the sum of W power K, or let's say N factorial, and minus 1 to the power N, and we want to take the sum from N to 0 to infinity. Okay, Mathematica says
it doesn't know.
It doesn't know.
It is what it is.
But now the Borel trick is just to do this. Divide by the factorial. All of a sudden, we get 1 over 1 plus W. Right? So we should maybe call this something different. So we just change variables from W to zeta, just to remind ourselves that we're not dealing in the same series, so to speak, right? We're really dealing with a different series at this point. And what you'll notice is that certainly this has a finite radius of convergence, but this function also has a singularity at zeta equals minus 1. Which means, okay, so first, let's look at two obvious facts, right? Inverse Laplace transformation of x power n x zeta is basically zeta power n minus, 1 minus n.
Minus 1 minus n.
Sorry, minus 1 minus n divided by gamma of minus n. So maybe, you know what, let me just change variables.
Singularity for...
Yeah, let me just do x bar. Just because what I want to do is take, instead of like an expansion around 0. Let's say we take an expansion around infinity. And then what you find is that zeta power n minus 1 divided by gamma of n, which is basically like the replacement trick by 1 over factorial, is like an inverse Laplace transformation of this particular term in the series. Right? So that's kind of the idea. Now, naturally, that means that if I were to take Laplace transform of zeta power n divided by n factorial, I think it's zeta x. We're basically, okay, well, let me simplify this. We're basically going to get back x power n minus 1, or minus n minus 1. So there's an overall choice being made about what kind of series we're doing. We're not expanding around 0, we're expanding around infinity, just to satisfy this. Okay, fine. We'll let it sort itself out. This should also be minus n, so fine, right? So you see immediately that there's a challenge that this function poses to doing the Laplace transformation if we're doing the Laplace transformation directionally, right? So normal Laplace transformation has a kernel which goes like e power minus zeta z or zeta x,
or positive
integral zeta 0 to infinity.
Yeah.
But I could actually take the integral 0 to e power I theta infinity, right? So there's like a direction I could in principle choose. If I made that
turning it into a Fourier, half Fourier.
Yeah, or it could be Fourier, or it could even just flip the sign, right? Because you could rotate all the way in the other direction. And in that direction, there's going to be a problem with this function. Now, if I was just doing this along the positive axis in the zeta plane, I'm okay. The negative axis is going to be an issue. So let's go and look at the basic example again with just the positive axis. And here you see you have just a simple meromorphic function with a pole at z equals minus 1. Now, there's another example that Marino goes through, which is this series, which is gamma k plus b divided by gamma b, a power minus k, s power k. This also has factorial growth of terms with respect to at least k. And the Borel transformation of this sum is 1 over z minus a to the power minus b. So the point is to go backwards. If we just do the Borel transformation, okay, so that this is the representation which is more akin to what we were doing. Remember, there was a minus n. So basically, instead of trying to Borel transform from t to w, do t to 1 over w. Like just change the power there so that we don't end up with this 1 over n thing that we were seeing in Mathematica. So this transformation reproduces f of w. Right? It reproduces a version of f of w, which is absolutely convergent for small w. Let's test that fact if you want to, if you're ready. So remember this kernel, okay? And let's share, switch to Mathematica again. And let me delete this.
And then I'll try to recap what we are.
Yeah, what the gymnastics are. Zeta over z, and there's an overall 1 over z. 1 over z. Infinity. Here we go. Okay, you see,
the integral in 4.51 also had this Borel sum as a function of t, which
so the
which
t,
is now the 1 over 1 plus
exactly
zeta. So because that is the first term, we removed the n factorial, and that was the Borel trick of removing that term and considering the properties of that new series. And now this has an 1 over z in the power, which is an essential singularity at z equals
Yes,
0.
very good.
And it also has this incomplete
Incomplete
gamma
gamma
function.
Yeah.
And Mathematica is also telling us that this only makes sense if z is positive, because I mean z equals 0 is
It's a
an
problem.
essential singularity, and I'm assuming this also relates to a branch continuity to the negative z somehow.
Well, we'll see. We'll see what happens.
We'll see.
So yeah, so basically the point is that the resummation procedure works. You know, it's just to say we'll get an answer that makes sense now all of a sudden, which
But-
beats the.
So why is it that it, in what sense are you saying that it works? Because it was a different series.
Yes.
Um,
So the point of resummation is really you're going to a different series,
Mhm.
but a better one.
Mhm.
So it works in the sense that there's a better series, which, you know, if you just thought of it as a series representation, that's not strictly true. But if you thought of it through all these analytic continuation tricks, in much the same vein as what you do with the zeta function, then there's a better representation of that series, so to speak.
So we didn't calculate the original series, but we
No.
are trying to build the relationship between this new series and the old series
Yes.
through an analytic continuation. That there's a parameter
Yeah.
that relates between the two series. I'm understanding. Is that the case?
Well, there's it's subtle as to understand exactly what the relations are between the two series, and we'll get to that because you see there are choices one needs to make about how to evade singularities in the complex, say zeta plane or T plane with respect to this parameterization. And that's exactly what Marinho comes to. So he talks a little bit about Poirier approximations, but so says, you see, say we had a function that had the following feature. The Borel sum of the function, so of the series rather, has singularities on the positive real axis. Now, the issue with that kind of function is that we're going to have to choose some contour or some contour prescription to avoid those singularities. And the two kinds of sums you get by avoiding the singularities one way or the other lead to different answers. Right? Because if you encircle a singularity above or encircle it below, then it gives rise to different contributions.
So where do these poles at the positive axis come from?
Well,
we had
let's
the 1
look at
over
that.
1 plus zeta just previously. That was a pole at -1.
Yes,
So
but
we are
if you
considering-
say you didn't have -1 power n, so let's actually do that.
So we are now looking at a different example.
Yeah, so let's go to Mathematica again and remove the -1 power n.
That would be 1 over 1 minus zeta. Now it has a pole at the positive axis. So
Exactly.
if we are integrating this over the positive z,
Yes.
according to this Laplace transform, that gives us an ambiguity because we can't integrate over the pole. So we have to choose a contour,
Yes.
which,
yes.
depending on which contour we choose, gives a different answer.
Exactly. And so here is the perturbative ambiguity in the words that Alexei Malekin was using in his paper that we were reviewing briefly. Right. So the fact that there was a perturbative ambiguity that canceled the non-perturbative ambiguity. You see that? That's where it came from. It came from the fact that there's a choice to be made in many of these situations about how you avoid the singularities in the zeta plane. So let's jump back to Marinho's notes. Here, you see that you could choose for the case where instead of the one pole you had two, you could choose a contour that goes like this or a contour that goes like that. And what one does is to look at the discontinuity between these two prescriptions. And the discontinuity is actually going to be the non-perturbative in W object. This is like the non-perturbative in W contribution. So, in other words, if you had a prescription for the contour, you resolve the ambiguity. And you'll see that like a median resummation prescription, for instance, is a way of resolving the ambiguity. Now, here he writes that explicitly.
So the difference between the two contours is an integral around each pole.
Exactly.
And by Cauchy residue formula, that is the
evaluation of the kernel on the pole. And now that kernel involved e power minus zeta over W.
Yes.
So you see, that's why you're going to get those kinds of contributions.
Yes,
because zeta gets evaluated on that. So it's going to be e power minus some number divided by W.
But that is an essential singularity. I mean, the
Yes.
Cauchy residue formula, we have it for simple.
But the singularity is in zeta, not in W.
In the
So because it's in zeta, with respect to that, there's no essential singularity. It's just exponential function. It's a complete function. So it's
it only has a simple pole, but now it is a function of
yes.
W.
Yes. Very good. Yeah, we're getting there. Nice. So here you see they go through the example we were actually considering before, which is the no alternating signs, just a sum n factorial W power n. Do the Borel sum, and you find that it's 1 over 1 minus t. Then do a Laplace transform, and worry that this is an ill-defined integral because of the pole at t equals 1. And you see the lateral summations differ by exactly what you mentioned, which is the contribution coming from a contour that encircles the pole, that here gives us through the residue formula 2 pi I divided by W e power minus 1 over W. And here, this has an essential singularity with respect to W, but the integral with respect to t. It's just a simple exponential function.
So t is going back a little bit up to 4.68 if we remove the n factorial, and instead of W called it t, this would be 1 over 1 minus t. So that's the t that comes from there. And now we are integrating this with different contours, and this gives us this essential singularity in the 4.70.
Yes. Very cool. So at this point, we have seen enough. Okay, well, we can talk about Borel transforms and large order behavior, but we have seen enough to maybe address the most important question of all, which is, what is an alien derivative?
Okay. Coming to aliens.
So we now jump to some very nice notes that I found actually maybe just a couple of years after this paper came out. It's an introduction to resurgence, trans-series, and alien calculus by Dorigoni. And let's jump to Stokes automorphisms and the alien derivative. Okay, so there's a slight change in notation as always, but we have enough information to be able to resolve all these issues. So what he has here is a series, psi tilde, which is the result of having done a Borel sum. So this is in the zeta plane where we have already divided out the factorials and resummed. It's some constant plus some phi tilde of zeta. And this then is related to a so the point is to then relate this to psi tilde of z, right? By picking, okay, so there's a generalization of what we call the Laplace transform, which is a directional Laplace transform, right? So instead of going from 0 to infinity, you go 0 to e power I theta. Infinity.
A certain direction in the complex plane.
Exactly. So there are two kinds of lateral Borel summations that they define here, which is you either go above or below all singular points along that direction, right? Ultimately, that's what we're interested in doing. We just want to choose a contour that avoids singularities. And then singularities tend to either be to the left or to the right, because we have a complex plane. And then if you have a line through it, then it just separates it into a left-hand side and a right-hand side, or an over and an under. So ultimately, whatever you do will result in there being two lateral resummations, one curly S sub theta plus and curly S sub theta minus, that correspond to choices of going above or going below.
Let me try to recap. So Laplace transform, instead of going from 0 to the real positive infinity, we consider it an arbitrary direction in the complex plane, but that integral can run over some poles or some singularity.
Exactly.
That with the plus or minus I epsilon, we will go to the left or to the right.
Exactly.
Modifying the angle a little bit to avoid the singularity in two different ways that we will now compare between them.
Exactly. So there's there's the same example that we were looking at, fortunately. 1 over 1 minus zeta. It's the best. And then you see the statement made in the previous notes, which is that the difference between the two resummations is a non-perturbative contribution, right? Very cool. Now let's talk about Stokes automorphisms. So the Stokes automorphism is frac G of theta, which relates S theta plus to S theta minus. What does that mean? It's just S theta minus the discontinuity over theta, right? So basically, the Stokes automorphism is 1 minus the discontinuity in that direction. A discontinuity is just the difference between the two evaluations, right? Now, of course, if S theta plus equals S theta minus, then the Stokes automorphism does nothing. And I mean, it only picks something up if there is singularity, right?
So this automorphism is going to is an automorphism between two sides of the contour. Whether we integrate it with a little bit angle on the positive clockwise or counterclockwise, but if it didn't go over any singularity, then
you wouldn't know the difference.
Then it's the same.
So in that case, phi tilde is called a resurgence constant. Okay.
An invariant of this automorphism.
Yes. But keep in mind this terminology resurgence constant, because it inspires what the alien derivative will do. So remember, the purpose of this is to understand what an alien derivative is.
So
right? Aliens are
there's an automorphism and there is a constant of this automorphism.
Yes. But what we will want to do, okay, so here's the most generic kind of situation one can have. So there's a direction and it has some number of singularities and presumably also branch cut or something. You either go over or you go under. And now what is the difference between the two? Well, the difference between the two are the discontinuities. You see, this is a nice depiction of exactly what that means. Very cool. So here comes the aliens. Now, the logarithm of this automorphism is called the alien derivative. Okay, which is kind of crazy if you ask me, right? I mean, like, let's break this down.
So what do we mean when we say the logarithm of this automorphism?
So you write the automorphism as the exponential of some operation. What is that operation? Well, it is the sum over singular points of e power minus wz. Now, z in this convention is 1 over w in the convention of what we were looking at before. So they've just chosen to start with series that go like z power minus n instead of w power n, just to deal with the Laplace transform conventions. The idea is that for every one of these singularities, what the discontinuity looks like is roughly some factors of e power minus wz or omega z times this delta w applied per n, so per singularity on phi tilde. So yeah, as the author of these notes admits, our definition is still pretty mysterious and unintelligible, which is why it's called, I think that's why it's called alien derivative. But as I promised, we'll take one at least. So let's just start with one. Okay. Say we had the Borel transform, not just containing a pole, but also a logarithm. We'll think very hard and maybe we'll come up with a function for which this happens. It's probably not that hard, but okay, let's say that there's a logarithm and there's a pole at location omega, right? And there's some terminology behind what alpha and phi hat are called. And so I won't go into that, but whatever. Let's assume that phi hat is entire along the direction theta, so no singularities. Then what we want to evaluate is the difference between the two resummation procedures, because that computes for us the discontinuity, right?
So here, what I'm understanding from the previous is that we are taking instead of going from the this Stokes automorphism to its logarithm, which will give us the derivative, we are looking at a system where we know the singularity in its logarithmic form. And then we will, in the next equation, exponentiate it to get the difference.
Well, it's more that the discontinuity, as in the exponential of the operation, is what's easy to compute. Whereas the logarithm requires some thinking. So that's just a basic point here.
Because the singularity in the exponent is an essential singularity in the...
Oh no, just because discontinuity is an obvious, like, it's the obvious thing to access, right? Whereas like one term in that, like, one delta sub w is it's kind of hard. It's just, I still don't know how to compute just that. I know how to do this though, right? So basically, what we do, right, in taking this difference is exactly what we mentioned before. Encircle the poles, and overlap the branch cut, and compute the discontinuity or the residue, right? Now, what happens in the case of the pole? Well, we just evaluate the we evaluate the kernel of the Laplace transformation at the pole, right? That's why we get the omega in the exponential. Same story for the logarithm. And again, there's a 2 pi I that cancels the, what you get by going over the logarithm. And you just have the integral here, which is e power minus omega z and the Laplace transform of the entire function. We did this shift, and this is what you get from the end. Now, there's only one singular point, meaning the exponential has only one term in the power series. This simplifies what the alien derivative is, and we can just read it off. And lo and behold, the alien derivative, it's just alpha plus phi tilde of z, which we can also represent in the Borel plane. You have a delta function instead of the one, and then you have phi hat, the original thing over there. And now let's go through one more example. This example is, it has this structure. And well, do you want to do this in Mathematica just to see what the resummation is?
So let's just see what this example contains. It's a function in Z. Also, the first two terms is a first order, second order singularity, and then we have a sum over n where this is a...
Yeah, so you don't think about this as a singularity. It's more that what we're doing is we're expanding in Z large instead of W, which would be 1 over Z small, right? Then basically we see that the sort of unhelpful part of the sum starts at n equals 2. And then, okay, I mean, we can run this through Mathematica, but
Yeah.
basically we're just going to find that the Borel transformation is of the format that we described before. What we're going to see is we're going to have a pole, an entire function, and a logarithm.
So this is the function that we get by removing the n factorial,
Exactly. And resumming.
which turns this into a
Yeah.
convergence series.
Convergence series, exactly. So at omega, the residue is minus 2 pi I a. And the so-called minor, which is the thing that you get by evaluating the discontinuity through the logarithm, is going to be 2 pi I times all of this evaluated at, let's see. Yeah, so this is just evaluated at zeta. So you're going to have zeta minus plus BW divided by W squared, or omega squared. So the inverse Borel transform of this is fairly easy to compute. And therefore, what is the alien derivative? It's this piece plus that piece. You see, remember this formula? Again, the case of having just the one pole. Very convenient. The generic case is a bit more complicated.
So what did 4.20 tell us about the original series that we had before the Borel trick? What is the meaning of this alien derivative at 4.20?
That's a very good question. So for the case where you have just the one pole, it's telling us what the series is that accompanies the essential singularity contribution to the original sum, right? You see that the result, like the coefficient of the alien derivative is e power minus omega z, right? So it's kind of like telling you what is, okay, maybe one way to put it, it's telling you what the perturbation expansion around the instanton background is. Right, so at least here it's just like a one instanton sector, and like what is a perturbative expansion around it? So that's kind of the meaning of the alien derivative. And now that's a good point you brought up, because perhaps that'll give us intuition for what to do in a case where we're slapped with this, right? Yeah, like multiple of these. And let's go up here. Right, this has the feeling, okay, it's kind of like maybe you have some multi-instanton sectors, and you have like the expansion around the multi-instanton sectors. So I think that might be what it's all leading to. But this is a derivative, though. You see, it satisfies various rules like a normal derivative does. And there are some manipulations you can do, but in general, it's pretty complicated to evaluate.
So each of these singularities corresponds to an instanton.
Yeah, it's like the action. So basically, the residue at that singularity is like the instanton action. It's the action of the instanton. Were we to think about the expansion parameters h bar, here it will be 1 over h bar in this convention. So this is the wisdom of the alien derivative. But perhaps what we can do is look a little bit further at what the what resurgence theory says about the relation between the Borel sum and large order behavior of the perturbation theory. Because I think that this is also an interesting fact. It connects back to what we were discussing with the optimal truncations. Right? So there's like this thing about how the Borel transform is actually sensitive, or how instantonic contributions are things you would start to notice where you get really far in perturbation theory, which is kind of cool. I mean, I think it's worth understanding it a bit slowly. So it says in many series appearing in quantum field theory and quantum mechanics, even if the coefficients aren't very simple, at large orders, they have an asymptotic behavior that is of roughly the format that we don't like. Right?
The factorial type.
Exactly. Then you see, okay, so this specific format apparently is the case for a quartic oscillator. So if you did like, what's it called, Rayleigh-Schrödinger perturbation theory for the anharmonic oscillator, that is potential omega x squared over 2 plus 1 over 24 omega, not omega, lambda x power 4. The perturbation theory is in Z, or not Z, but in this is the coefficient of the lambda expansion, say energy levels, right? So the Borel transform for such series will be of the following form. This was just the example that was shown in the notes, right? So you take this, divide by k factorial, sum over k with some z power k. I'll just evaluate the following. Yeah, the above expression shows that the Borel transform encodes data in 4.71, determining the large order behavior of the coefficients a sub k, independently of whether the series is Borel summable or not. So the factor a in QM is the action of the instanton. Remember, it was appearing as e power minus a over w in these notes. Exactly. So that's what we relate to what we were discussing. And is given by the location of the singularity of the Borel transform, which is closest to the origin, right? Which is like what we just realized with the leading alien derivative. Leading alien derivative is always e power minus omega z, which is like omega over w from this perspective, and that omega is the location of a singularity on the Borel plane, specifically the one that's closest to the origin. B in the exponent characterizes the branch cut pole structure of the Borel transform at z equals a, right? Because this is basically like a rational function of the complex plane, and you see that B tells you that there's going to be a branch. You need to involve a branch cut in this because who knows what B is. So the large order behavior of a divergent series is controlled by the singularities of the Borel transform. So you see these instantonic sectors. So what we did was we looked at really large order behavior and then evaluated the Borel transformation of that piece and inferred that there's necessarily going to be like singularities that the large order stuff is going to give rise to. So that means that the singular behavior of the Borel the Borel sum tells us about large order behavior of the divergent series. So this is the reason why you need to go to really high orders to realize, oh, well, there's an instanton. I mean, this is kind of like also how you maybe discover D-branes if you're doing just string perturbation theory. Go to really high orders and you're like, wow, okay, it's maybe branes or something. But okay, let's look at the general formula that Marino is talking about here. So let's give a general formula for a quantitative expression for the relation between large order behavior and Borel transforms, right? So let's see that this is true in general. Say that the Borel sum is b sub k z power k, meaning that the original coefficients had a k factorial in front of b, right? Write k factorial with the integral representation of the gamma function, right? And then look at this part and write it in terms of the Borel sum. So basically what you want to do is say that, well, b sub k all came from doing a Borel transformation. And there's basically, so what you're going to get is the following expression, right? Well, the trick here is to say that if I looked at du over uk plus 1 b sub s of u, the kth term in the expansion of b sub s will lead to a simple pole in u. And when we look at the contour integral around the origin, then the residue will be b sub k. 2 pi I times b sub k. So you see, you divide by 1 over 2 pi I. So this is like a general trick to say, I want to capture order k. I know that it's a series. How would I do this using contour integration with respect to this expansion factor? Let's divide by u power k plus 1, right? And then we'll look at the contour integral around 0, which is just an evaluation of the simple pole, right? The simple pole arises at b sub k.
So we are rewriting the coefficients in this small bk.
Yes.
As how would we extract them if we had the full sum?
Exactly.
Considering the Borel sum in 4.73 as a generating function.
Absolutely.
As a generating function for these coefficients bk,
Yes.
And now when we write AK in terms of this gamma function representation, how do we extract BK? It is through, I mean, using the generating function to
Yes.
extract the small BK from the Borel, the full function.
Very good. Very good. Good. Cool. So by deforming the contour around the origin to the contour gamma encircling the cut and the singularity. Okay, let's go to figure 23 just so we know what's going on. U equals A is where problems start, right? Because the function of interest is 1 over, 1 minus, 1 minus Z over A to the power B, right? Which means there's a branch cut and a pole starting at Z equals A, right? Which is written as U here, fine. There's a contour encircling the origin. What we're going to do is push it over here to turn it into one of these Stokes contours. Remember the Stokes. So.
And this is not just a pole, it is a full branch cut.
Yes. So the idea is to start here. Okay, there's some gymnastics going on that we have to kind of look at carefully. Integral dt, 0 to infinity, still true. Then now U has become S for whatever reason, and there's
just rename it.
Yeah, and
but we are changing the, I mean, 4.74 to the next equation. We are doing what you showed in this figure above.
Yes. So the contour integral around 0 has gone to the contour integral over gamma.
Over the branch.
Yeah. And now the idea is to change variables to combine T and S into U so that we have the following structure. So we have Z and, okay, let's go a little bit more slowly then. We've taken Z to be U over T. Okay. I suppose that it means S over T because, well, U is here, T is here. This probably should have been written with respect to U.
I think so.
So we want to take T over, so Z is U over Z, T is U over Z, okay? And presumably this S should be U. So the result of that change of variables gives us a formula like this. Okay. I'm still struggling to see in my head what's happened here. T is U, okay, I see. So T has gone to U over Z. That means that T power K is U power K over Z power K plus 1. There's another S power K plus 1.
So in the first equation, if we just rename S to U as it was originally in the previous one, when we write T equals U over Z, that U to the K and in the denominator, U to the K plus 1 cancel each other. So that's why we get the Z to the power K plus 1 on the right-hand side together with that. So it's, yeah.
Okay, cool. So it's just a matter of keeping U instead of S here, and then it'll be, yeah,
it's just combining this. I mean, here we have T over U in the first part of the equation, and that T over U we'll call it
1
Z.
over Z. Yeah.
1 over Z.
Yeah. Good. Okay, we're on the same page now. And there's a cost for changing, I guess, the integration measure, which gives you a 1 over Z.
And to recapture one of these, the T had come from the gamma function expansion.
Yes.
And the S or U had come from the generating function.
Yes. Exactly. Very
and
good.
Now we are combining those two powers into one
object. Nice. Okay.
One parameter.
Great. And now they say that we have assumed that the behavior at infinity is such that no contribution is there to take into account. This has to be proved on a case-to-case basis, but at least for the example they showed, that's true. So gamma is that kind of discontinuity contour as we described below, as we described before, right? The C naught plus and C naught minus. right? So it's basically like an evaluation of a discontinuity over and below a branch cut. And therefore, the contour integral splits into a difference. But what is this, you may ask? Well, this is the kernel of a Laplace transform. So it's the difference between the two directional Borel sums, so the directional Laplace transformations of the Borel sums, which is what we encountered before, right? But now we've not just done that, right? But that's one aspect, that's one integral, this integral. There's also this integral. What is that doing? Well, it's capturing the order k term, right? It's the generating function trick all over again, right? That gives you a sub k, right?
The coefficients in the original
Exactly.
that we are trying to understand.
Exactly.
The divergent one.
Yes. And that's why we have a general relation between what? This piece, which has intimate knowledge of the singularities in the Borel plane, and a sub k, right? Which knows about the large order behavior of the perturbation series. Nice. And then they just test this on the expression that they have, and they obtain the behavior that they expect.
So the coefficients of this original divergent series that is actually the integral over
it's like
the integral
the
over the difference
of the alien derivative. So yeah, this is what the alien derivatives capture.
It's a singularity. It's a branch cut that.
I mean, it's really
the difference between them is this large behavior of the coefficients.
Yes, exactly. Now, if you just knew the formula for a sub k that you had before, you would think, well, it's some hugely divergent factorial thing. Well, who cares, right? But the point here is that no, you didn't remember that there was actually these instantons that contributed to it, right? So you see that a sub k is actually sourced by the instantonic contributions. So that is basically the relation between Borel sums and large order behavior.
What I'm realizing here is that we are still not computing the original theory. We are because the original theory is divergent, okay, but it is a power theory, and in physics we encounter power theories a lot, especially when we do a perturbative expansion. It usually isn't convergent, but we want to understand the coefficients of this using a resummation. We want to express them. How do they relate to these non-perturbative effects?
Exactly. Yeah. And that is precisely the point. The point is that what we originally had, right, is not what we thought was a power series isn't actually a power series. It's actually what's called a resurgent trans series. So let's briefly jump to those notes where a very general definition is given of trans series. Okay. It's a bit of a circular definition, but I think it'll suffice for our purposes. To say a log-free transmonomial is a symbol of this form, right? So T itself is a log-free trans series. It's a purely log-free trans series, and A is real.
So let's try to understand this. Log-free, so it doesn't contain a logarithm.
So far, no logs. Yes.
So far, no logs. Monomial. I'm seeing there.
It means it's a piece of an expansion. I think it's one term in an expansion.
Transmonomial,
which is just one of those circular things, which will become, we're going to describe a trans series, so it's going to be a transmonomial that then turns into a trans series.
Yeah. Okay.
Yeah. And now the point is that there's a hierarchy between these monomials, which is that ZA1 e power T1 is greater than ZA2 e power T2 if either T1 is greater than T2, or if both of these T's are the same, but then A1 is greater than A2.
We first look at the e to the T, the exponents. If one is larger than the other, that's defines the hierarchy.
Yes.
Otherwise, we look at the power of the monomial.
Well, I see here's the hierarchy, right? It's e power z is greater than e power z, which is greater than z power minus 2 e power z, which is greater than z power 10, which is kind of in keeping with our
First the exponent, then the monomial.
Yes.
That we look at to compare.
And a log-free trans series is just a sum of trans monomials.
Of such terms that are combined from monomials and exponential terms.
Exactly. The height of a transmonomial is defined as the number of times we compose the exponential, right? So if you have e power z, then that has height 2. If you just have e power z, like in the instantonic case, you have height 1.
So it's
it's just funny to see that they admit we just defined the transmonomial using a notion of a trans series and then define the trans series starting from transmonomials in an Ouroboros manner. But it suffices for our purposes, I think.
I mean, it is worthy, but it was log-free because if there was a log in the exponential, that would make it no exponential anymore. So
exactly.
That's why it was log-free. But we have exponentials are a hierarchy of exponentials over the monomials.
Yes.
So we want to be precise about what we mean by exponential. We want to keep it log-free so that it doesn't go back to a monomial.
Yes.
And we can also count multiple exponentials. E to the z will be hierarchically over e to the z.
Exactly. Now, you know what's nice is that in physics, typically, if we're just looking at the example of, say, ground state energy of the Sine-Gordon theory or like the double well, then you're just going to have height 1, meaning you either have exponentials, so you have instantons, multi-instanton sectors, or you have these kinds of polynomials. So let's just look at one instanton sector, then this is one term in the expansion around that one instanton sector, right? Now, there's a lot of talk about the various magnitudes and their various properties, but in quantum mechanics, this is essentially, we basically just have this structure. So there are logarithmic corrections to an otherwise height 1 log-free trans series, and those logarithmic corrections are related to what we talked about, that is the quasi-zero mode integrations over the distances between the various instantons and anti-instantons and so on. So in addition to what we would normally have, which are like height 1 log-free trans series, we have these log factors. The fact that it's height 1 means that it's easy to order the log in the hierarchy. I mean, if it gets higher, it gets sort of complicated, but you have logs and you have these things, which is great, right? So you have e power minus s to the power n, and then so that sets how many instantons we're talking about. And then we have these things that are like perturbative expansions around the instanton sectors, and we have the logs that know about the separations between the instantons. And you see, the logarithms start appearing only at n equals 2, which is the 2 instanton sector. And the reason is that in quantum mechanics, the log sector comes from the integration over quasi-zero modes. And that's precisely what we heard in that discussion of the BPC regularization.
This sounds like it goes back to this attraction repulsion between instantons and anti-instantons. Only if we have at least 2 of them that
exactly
we run into these ambiguities or divergences.
Exactly. So this was a brief intermezzo, but now I just wanted to like briefly run through that's very nice paper where the Borel resummation is taken into the path integral. Good, very cool. So I'll just go over the expression, the actual mathematical expressions, and we'll try and appreciate the effort. So start with the path integral. There's a free and interacting part. The idea is that if you wanted to compute amplitudes of this path integral, the result is necessarily going to be a perturbative series in the coupling constant. The issue is that in most cases, this has 0 radius of convergence, so we do the Borel sum. And then the original series is obtained by doing a Laplace transformation with respect to G, right? And as we discussed, there's going to be ambiguities that need to be resolved. Now let's put all this into the path integral. So you see, what's nice is that we know whatever we do with this, the result is going to look like this. Which means that whatever we do to this, we should do to this. Okay, what does that mean? In order to go from the original sum to the Borel sum, we can use the following representation, integral representation of the dividing by factorial trick. Right, so you introduce e power z, take dz over z power n plus 1. And what you're going to notice is that if you thought about this carefully, the same argument we used for collecting the residue
from the generating function.
Exactly, the generating function. This is like the generating function for 1 over factorials, right? E power z, because it's z plus z squared over 2 factorial plus z cubed over 3 factorial. So if I want 1 over, say, k factorial or n factorial, what am I going to do? Expand this to order n, divide by n plus 1, zn plus 1, and then look at the contour integral around the origin. That's going to give me 1 over n factorial.
So the exponential, we are extracting the factorials from the power series of the exponential.
Absolutely.
We use the generating function trick again to write down this Borel transform series that we divided by n factorial, but now we are writing an integral representation.
So here's the fun that it's a fun observation that Millikan made, which is to say, okay, this is like Cn g over z power n, which means wherever there was g in the original Lagrangian divided by z. You have dz over z e power z. Okay, and that's it. There's the Borel Lagrangian for you.
It was just a rescaling of the coupling constant with this.
Except now you see there's an addition here, and then there's this dz over z. So it's a weird, it's a kind of like it's like a weird kind of like Laplace transformation, some Legendre transform with respect to the coupling itself in some weird way.
Why is there a plus z?
Because there's an e power z here.
That
we're just absorbing that into the action.
We are in the exponential, the new action, so that's absorbed into the action.
Yes.
And then we integrate over this. I mean, there's the integral carries over.
Yes.
And this is the new path integral, the new partition function, except that we looked at how does this transformation, this Borel transformation, is shown in the action in the transformation of the action, the Lagrangian.
That's great, right? And you see, now all the subtleties go into z. Like, there's an integration over z, and you can say, well, I can compensate for whatever monkeying I'm going to be doing with g by just monkeying around with the integration over z. So it's like a constant background dilettante field, right? So that's kind of the idea. And you see, you could write it as e power. You could write log z as phi, and it would literally look like a dilettante. And it appears in exactly the same way. And now we can say, well, let's go back, right? So let's choose a contour. So if we had linear dependence on the coupling, say we had phi-4 theory, and we're just doing this with like the lambda in front of the phi-4 term, then the following will happen, which is you would want to do the Laplace transformation, which shifts z in the following manner. And you're going to get z plus g naught times s interaction in the denominator here, which means that the poles in the z plane are shifted essentially by the interaction part of the action.
You're doing a Laplace transformation on g?
Yes, you see, because we needed, for now we're leaving z alone. We're doing the Laplace transformation with respect to g because that's our trick, right? That's like our trick. But now, what's that going to do? It's going to give us 1 over z.
Shifting this this pole, this singularity.
And then, well, what are we going to do now, right? just look at the residue at this pole, and that's gonna give you, it's gonna give you what it's gonna give you. So note that we had to actually push the contour of Z to capture the contribution of G naught S. Now it's subtle because it's all happening within the path integral, which means that the choice of contour doesn't depend just on, it might depend on the field configuration that's being considered. And so
it's a shift by the action, which we, well, path integrate over.
Yeah. And so, yeah, this is a fascinating part of the story. And then he goes on to describe some kinds of funny word identities one gets by shifting, like playing with Z, doing deformations of Z. And then he goes into applying that method to compute the instant-on contributions and shows that, well, everything we had before can be recomputed by doing the appropriate manipulations involving Z and computing the instant-on action.
Going back to just above this shift of the singularity by the action.
Yeah.
Since the action is now outside the exponential, it looks to me like this would have some Feynman diagram expansion, would it? Because there's
Yes,
some there's some function of the path integral variable that is now outside, and
it's like the path. So what you're going to be computing is the expectation value of 1 over, or transition amplitude, but let's say we're doing everything Euclidean, is the expectation value of 1 over Z plus this, right? Which is interesting because these kinds of expressions appear in like the relation between matrix models and quantum mechanics. So like the spectral resolvent has an expression like this. The expectation value of 1 over Z minus H, or Z minus M. So I do wonder what the
resolvent also has these branch paths that
exactly. So yeah, it's a really interesting question as to exactly how these things are related. And yeah, so I'm really excited to see where this goes. So this is I just wanted to like shout this paper out. And okay, I mean, one other thing that's pointed at in this paper is how do you extract the large order behavior now from the perspective of just the action? And it's our favorite trick, right? So Borel transformation. Okay, so the idea is this is apparently pioneered by Lipatov to show that we want to estimate what happens at order lambda naught to the power n in some scalar field theory at very large n. This can be done through a classical calculation. That's a claim. Sounds crazy, right? We'll see what that means. So the very high order behavior in perturbation theory of some series, a classical calculation that can capture it. So same trick. But now we push this into the exponential. And then, because n is large, we can evaluate it at a saddle point. And what Lipatov did was show that there's a configuration called the Lipaton, which captures that behavior.
Nice name.
The saddle bound value for lambda naught is negative, apparently. And we can actually go and look at okay, so let's see that this isn't like completely nonsensical thing to do. So let's take exponential. Let's just take the exponential function and say we're gonna add. So say we have the exponential z lambda, and we'll
discover some bosons.
This is it's the poor man's Lipaton. You can't afford a Lipaton, then you're gonna have to deal with whatever I find here. Right? So this is like the formula. Now what we're gonna say is that there's a contour integral being done over lambda. But we're gonna evaluate this at the saddle point, so that means we're gonna solve okay. You see, you get this funny behavior. We know that at order n, exponential z lambda is going to have a coefficient in z that goes like z over n, z power n over n factorial. So you see minus n.
Minus n.
Okay.
So e to the logarithm becomes n over v over minus n.
Yeah.
So it has z over 1 over v to the power minus n, which is z to the n.
Exactly. So, sorry about that. But you see, Mathematica knows the Stirling approximation. And indeed, we're getting what you just described. You have e power n, and you have the log z over n, which is basically, since it's in the exponential, you say that it's all multiplied by n, so it's z over n to the power n times e power n, which is just exactly what you have here, right? So it's not an insane thing to do, right? And that's amusing to me, at least, right? That there's a classical calculation
For the very large order of the perturbative expansion.
Now that sounds okay. It sounds a bit odd, but instantons are classical saddle points. And then what we just learned about the relation between instantonic configurations, that is Borel sums, and large order behavior of the series. They're related. So we just come full circle. It's not yeah, okay, so that's basically the resolution. Just kind of like appreciate it. It's nice. This basic fact. So yeah, that's
well, we learned about how the aliens are.
We can do one alien derivative. Maybe in a year we'll be able to do two. So we'll, yeah. So, but I think the next time we talk, we should talk about the matrix models. But anyway, for all of you, if you're still listening, you should subscribe, leave a comment, like, and
hit the bell button.
Yes, hit the bell button. This was Theoretically Podcasting, and I will see you all next week. Thank you for your attention.